In this lecture, we will talk about a single problem, and that is traveling to Mars. So the question is, if we're here on Earth orbiting the Sun, Mars is on an outer orbit. We want to know how to send a spacecraft or a space capsule with people on it to Mars using the least amount of energy. This is important because it takes a huge amount of energy to power rockets and to send them through space. So doing this in an energy efficient way makes it possible. So you might think, well, maybe I'll just wait for the Earth and Mars to be closest, and then I'll just jump over. Maybe that'll be the least amount of energy. So it turns out that's not the case. And the reason that that's not the solution is that it doesn't take advantage of the Earth's orbital velocity around the Sun. So when we launch a spacecraft from the Earth, it inherits the velocity of the Earth through space. If we want to just go from here straight over to there, we would have to have a velocity vector that went straight up, and we would have to somehow counteract this velocity. So we would have to have a thruster, a prograde thrust, opposing that, and then also boost it out of our orbit radially. And so that just doesn't work. Also, Mars will be moving in its orbit, and so it won't be there if we just send it straight across. The answer is that the path that uses the least amount of energy takes pretty close to the longest distance, which is a little counterintuitive. So if you want to get to Mars here, then the best thing to do is launch the space probe when the Earth is on the exact opposite side of the solar system to send it all the way around over to here. That's called a Hohman transfer. And that's what this lecture is going to look at. So here's how this works. We want to launch the spacecraft from down here when the Earth is down at the bottom of the orbit, and we want it to reach this target position here. Now Mars isn't there because Mars is also orbiting around. So basically what we're going to do is launch the spacecraft. It's going to go up and get to this point. Meanwhile, Mars is also moving through space, and you hope that Mars and the spacecraft both arrive at that point simultaneously. And that's what rocket scientists actually do at JPL. They do timings like this. So we are going to launch the spacecraft with a prograde velocity boost. That means we're launching it in the direction of the Earth's motion. So the velocity of the probe will be slightly larger than the Earth's circular velocity. And you're going to send it into an elliptical orbit. Okay, so we're going to do a little cartoon animation here. We're going to launch the probe, and we're going to watch its motion relative to the Earth and Mars. So in the next step, the Earth is moved around a little bit, the probe is moved, and Mars is moving. The Earth's here, there goes the probe, there's Mars. The probe is getting closer to Mars, and then again, hopefully Mars and the probe get there at the same time. Meanwhile, the Earth is like over here now. So what we want to do is find the semi-major axis and eccentricity of this transfer orbit, that elliptical orbit. Find how long it's going to take the probe to reach Mars. Find the velocity that we need to launch the spacecraft at. And then the question is, well, now what happens if suppose it was a manned mission, how do you get the crew back to Earth? Like when can you launch them back? All right, so let's make some definitions. RE will be the radius of the Earth's orbit. RM is the radius of Mars's orbit. VE is the circular speed of the Earth. We're going to assume that the Earth and Mars are going around the Sun in circular orbits to make the calculation simpler. JPL scientists don't make that simplification. They take their actual orbit. VM is the circular velocity of Mars. And we'll say that delta V is going to be that little boost that you give the rocket to kick it into that orbit. Now, once the space probe comes out here, it's going to be, this is going to be at the aphelion point, so it's going to be going much slower here than when it was launched. And it turns out that it'll be going slower than Mars is also. So if you'll need to give it another prograde boost to actually catch up to Mars. So it's going roughly the same speed when it arrives. All right, let's calculate some of these parameters now. When we launch, looking at the diagram, this is going to be the closest point of the Hohmann transfer orbit to the Sun. So we're launching it at perihelion. So the perihelion distance of the transfer orbit is just equal to the orbital radius of the Earth. When it arrives at Mars, it'll be at aphelion. So the aphelion distance will be the orbital radius of Mars. So now we can very easily calculate the semi-major axis of the ellipse. Remember that the total distance across the ellipse is twice the semi-major axis. And by looking at this diagram, we can see that that distance is just going to be the radius of the Earth's orbit plus the radius of Mars's orbit, or in other words, the perihelion distance plus the aphelion distance. So 2a equals rp plus ra divided by 2. You get an expression for the semi-major axis. Plug in the values for rp and ra. And the semi-major axis of the Earth is 1 AU. Semi-major axis of Mars turns out to be 1.524 AU. And then calculate that. So it turns out that the semi-major axis of the transfer orbit is going to be 1.262 astronomical units, halfway between the semi-major axis of the Earth and Mars. So the travel time is going to be, well, it's going to be half the period, right? So the period of an elliptical orbit is how long it takes the object to go all the way around and then back to where it started from. Since we're only going from perihelion to aphelion, it's going to be half the period. So to get period, you can use Kepler's third law, the simple form where we've set that constant k equals 1. So in other words, p is a to the 3 abs power. Just plugging in the semi-major axis is 1.262 AU. Gives us 1.42 years. So converting that to days, that's like 518 days. And then dividing that by 2 gives us 259 days. So that's a little under 9 months. So it'll take the crew, or any mission to Mars, about 9 months to go from here, where the Earth's orbit is, over to Mars using this Hohmann transfer. Okay, let's now calculate the orbital eccentricity. So because we already know the semi-major axis and the perihelion distance, it's very easy to calculate the eccentricity from this equation. So solve for E, 1 minus perihelion distance over semi-major axis, plug in. So we get an eccentricity of 0.208. We can use that eccentricity now in the equation for the perihelion velocity. So we're plugging in, let's see here, the mass of the Sun is 1.99 times 10 to the 30th kilograms. Now, you have to be careful here. This equation, everything has to be in MKS units. So, you have to plug in G in MKS units, mass of the Sun, and the semi-major axis also has to be in MKS units. So it's 1.262 AUs, but then 1 AU is 1.5 times 10 to the 11th meters. So this is the semi-major axis in meters. And so when you do that, you get 32,700 meters per second, and then I converted it to kilometers per second. So 32.7 kilometers per second is the total launch speed. But a lot of that is actually taken up by the Earth's orbital velocity. So you don't have to launch it at this extra. Let's see. So the circular velocity of the Earth, remember, is square root of gm over a, which turns out to be 29.78 kilometers per second, where we've plugged in 1.1 AU, so 1.5 times 10 to the 11th meters here. So we can see that the velocity boost, what you have to actually give the probe, is the difference of these two values. And so that only turns out to be 2.9 kilometers per second. So, 90% of the speed is actually already provided by the Earth's motion around the sun. And that's why this is a fairly low energy solution, because you're making use of that orbital velocity of the Earth. You're just giving it a little nudge out of that trajectory, out of that orbit, to kick it up to where Mars is. By the way, this 2.9 kilometers per second works out to be 6,490 miles per hour. Since the velocity of the Earth is about 10 times that, the velocity of the Earth is actually going about 64,000 miles per hour as we orbit the sun. So if you figured out the kinetic energy, it turns out that 83% of the spaceship's kinetic energy is already provided by the Earth. We just have to add another 17%, I think. All right, what about the velocity once we get to Mars? How fast is it going to be going? Same calculation. Actually, we can save ourselves a little bit of work by using this equation. The ratio of the perihelion to aphelion velocity is given by this. Solve for the aphelion velocity, plug in. We see that the aphelion velocity is 21.5 kilometers per second. Repeat the circular velocity for Mars. We find it's going at 24 kilometers per second. And so we've got to have a second prograde boost of 2.6 kilometers per second. Okay, so finally let's look at timing. So again, if we're launching the probe here when Mars is over there, we're going to say that that's at time t equals 0. A way to figure out the timing is relative to opposition. So after you fire the probe, it's going around, Earth is moving and Mars is moving. The Earth has a shorter period than Mars, and so it'll catch up and lap Mars. So at some point, the Earth is going to pass between the Sun and the Mars, and so we'll say that Mars is at opposition here. And the calculation is fairly simple, but I'll just show the result. That it turns out that it takes 95 days, that the launch of the space probe has to happen 95 days before opposition in order for the probe to arrive at Mars. Okay? So the total time it takes the probe to go from here all the way over to where Mars is 259 days, but the launch date has to be 95 days before Mars is in opposition. So what about returning to Earth? What do you got to do? Well, what you have to do is wait for the next opposition. And to figure that out, you can figure out what the synodic period of Mars is. So this is from chapter 1. The synodic period is just 1 over the period of the Earth minus 1 over the period of Mars. So it turns out to be 780 days. So the Earth and Mars line up once every 780 days. Finally, it turns out that the total duration of the mission works out to be that synodic period of how long it takes the Earth and Mars to line up at opposition, 780 days, and then you've got to add on 2 times that 95 days, that window for launching. So you got to launch from Earth, 95 days before opposition. So a total mission duration of 970 days, which is about 2.7 years. So if you're planning a mission to Mars, you got to kind of really commit, right? I mean, the minimum amount of time to go to Mars and come back is almost 3 years. And if something goes wrong and you miss your launch window for returning, there's a few things you can do, but if you really mess it up, you're going to have to wait for that next opposition to occur. So here's what it looks like if you launch from Earth, from here to arriving back, that's that 970 days. Here's the opposition where the Earth and Mars line up, that's 780 days here. You're traveling in this window here, you're traveling in this window there, and then so you've got a little over a year to actually be at Mars. The rest of the time is going to be spent in the space capsule, transiting to Mars and then coming back. Okay, so that's it. That's it for this unit. We'll be talking about the interaction of light and radiation in the next unit.